For almost 100 years, physics has been staring down its biggest challenge. How do you unite the two pillars of modern science? You've got the bizarre, probabilistic world of quantum mechanics and the vast geometric universe of general relativity. They both work perfectly in their own domains, but they just don't talk to each other. Well, now, a really groundbreaking paper by Alexander New, Amaya, Odilon, Kosso, and their team is proposing this breathtakingly elegant solution. The idea isn't to force them together, but to show that they've been following the same hidden logic all along. So let's break down how this incredible idea actually works.
Here's the game plan. First, we'll dive into why these two theories have been at odds for so long. Then we'll get into the beautiful core idea of this new framework, the delta-omicron transformation. From there, we'll see how it brings physics together at the tiniest possible scales, how it might just solve some of the biggest paradoxes in the universe, and, crucially, how we could actually test it. And finally, we'll ask the big question: is this a new theory of everything?
So, what's the actual problem here? Well, you can think of modern physics as running on two totally different operating systems. One's designed for the super small, and the other's for the incredibly large. And if you try to get them to work together, say inside a black hole, the whole system just crashes.
And this really gets to the heart of it, right? On one side, you've got quantum mechanics. It gives us this fuzzy, jumpy world of particles and probabilities. But on the other side, general relativity paints this picture of a smooth, predictable universe where gravity is just the elegant curving of space-time. The issue? When you get to the most extreme places in the universe, like the very beginning of the Big Bang or the center of a black hole, you need both theories to work at the same time, and their descriptions of what reality is are just completely fundamentally incompatible.
Okay, so this is where the paper from Gu and Kosso comes in and suggests something really radical. What if we've been looking at it all wrong? What if these two theories aren't actually separate things at all? What if they're just two different results of one single, much deeper process of transformation?
The authors kick this off with a really beautiful analogy they call the general relativistic principle. Just picture a simple pointy shape, a triangle, which they call delta. Now, what happens if you just keep adding more and more sides to it? Forever. You're going through an infinite process, right? Well, eventually, that pointy, discrete shape becomes a perfectly smooth, continuous shape, a circle, which they call omicron. This simple journey, from a discrete thing through an infinite process to a smooth, bounded thing, that's the core logic they think the entire universe is built on.
So this is the central claim, right here. Physics isn't really about static things or fixed laws. It's about this constant transformation. The triangle, delta, that's the discrete, fuzzy quantum world. The circle, omicron, that's the smooth, geometric world of gravity and classical physics. And that symbol in the middle, infinity, it's not just a concept. It's the engine, the process that connects the two.
Okay, let's see how this actually works. Take quantum mechanics. You start with the wave function, which is like this cloud of all the possible places a particle could be. That's our starting point, our delta. The process of measurement, which is what forces that cloud of possibilities to collapse into one single answer, that's our infinity process. And the final result? A single definite location, a concrete reality, that's our omicron. See, the pattern fits perfectly.
And what's so wild is that you can see the exact same pattern in general relativity. Here, our delta, our starting point, is just all the stuff in the universe, matter and energy. The process, our infinity, is dictated by Einstein's field equations. They're the rules that tell space-time how to bend. And the end result, our omicron, is the actual curvature of space-time itself, the thing we experience as gravity. It's the same logic, just playing out on a cosmic scale. It's been hiding in plain sight this whole time. All right, now for the million-dollar question. If this whole framework is right, it has to hold up where it matters most, at the Planck scale. This is the tiniest, most high-energy level of reality you can imagine, where the rules of quantum mechanics and gravity become equally strong. It's their ultimate showdown. These are like the fundamental pixels of our universe. The Planck length isn't just a small distance, it's the smallest possible distance. The Planck time is the shortest tick of a cosmic clock. It's at this impossibly tiny, mind-bogglingly energetic scale, a scale where a single particle has enough energy to collapse into its own black hole that any real theory of everything has to work. There's no hiding. And this is the absolute heart of the paper's proof. The authors basically asked two really simple questions. First, according to quantum mechanics, what's the fundamental limit on uncertainty at the Planck scale? Second, according to general relativity, how much stuff do you need to cram into that same tiny scale to make a black hole? And the answer is just incredible. When you do the math, both theories give you the exact same answer. They literally arrive at the same statement. At the absolute limit where everyone expected them to break, they instead start speaking with one voice. Okay, so this is more than just some neat mathematical trick. A true unified theory needs to do more than just look pretty on paper. It should solve the deep, nagging paradoxes that have kept physicists up at night for decades. And this Delta-Info framework claims it can do exactly that.
First up, the singularity. General relativity tells us that at the center of a black hole, everything gets crushed into an infinitely dense point where our laws of physics just stop working. But in this new model, space-time itself has a kind of springiness. The paper uses this fantastic analogy of a quantum trampoline. It bends, but it doesn't break. It resists being crushed into infinity. This equation here shows you how. That tan function basically acts like a brake. As the classical curvature tries to go to infinity, this formula puts a cap on it, ensuring the real physical curvature never goes past the Planck limit. No singularity means no broken physics. Problem solved.
Next up, the black hole information paradox. This one's a biggie. A fundamental rule of quantum mechanics says that information can never be destroyed, but black holes seem to act like cosmic paper shredders. Well, the Zozo framework says, not so fast. The information isn't lost, it's just transformed and stored. It gets encoded in the black hole's total information content, or its entropy. And then, over billions of years, it's slowly released back out. So a black hole isn't a trash can. It's more like a quantum safe, keeping everything that falls inside perfectly preserved.
And then there's maybe the weirdest one of all, the problem of time. In a lot of attempts to unify physics, the final equation that's supposed to describe the entire universe has no time in it. It suggests we live in a static, frozen block universe. But here, time isn't a fundamental thing that exists on its own. Instead, time emerges from the transformation process itself. The very flow of time that we all feel is nothing more than the universe constantly progressing through its endless chain of delta to omicron transformations. Time is the motion of change.
So what's the difference between a cool idea and actual science? You have to be able to test it. And here's what makes this framework so exciting. Unlike a lot of other theories of everything, this one makes real, concrete predictions. It gives us things we can actually go out and look for.
So what should we be looking for? Well, the theory predicts we might find tiny, unexpected wiggles in the afterglow of the Big Bang, or strange anomalies in the gravitational waves we detect from merging black holes. But maybe the most direct, most exciting prediction is that it changes one of the most sacred rules in all of physics, the Heisenberg uncertainty principle.
Okay, take a look at this. The first part of the equation, on the left, that's the standard uncertainty principle you learn in school. But look at the new stuff on the right, inside the bracket. Those are the corrections that come from combining quantum mechanics and gravity. Now, in our everyday world, these terms are so tiny they're basically zero. But if you get to energies close to the Planck scale, they suddenly become huge, and they would fundamentally change how uncertainty works. If we could ever detect that deviation in a particle accelerator, it would be the smoking gun for this theory.
So, we've walked through the core idea, we've seen how it brings the two theories together, how it solves major paradoxes, and even how we could test it. All of this has been building to the paper's final, audacious claim, a single, unified formula for the entire universe.
This quote from the authors, New and Kosso, really captures the huge shift in thinking here. The universe isn't a collection of static objects just sitting around in space-time. The universe is the transformation. It's a single, dynamic, ongoing process where quantum possibilities are constantly becoming geometric reality.
And here it is, the master equation. On the left, that psi_universe symbol represents the quantum state of everything, the whole shebang. And on the right, it tells us that this total state is the result of a single transformation process, T. And what is it acting on? This is the wild part. It's acting on a combined state where quantum possibilities and the geometry of spacetime are fundamentally entangled. They're linked together, influencing each other from the very start. It means reality isn't quantum or gravitational. It's quantum gravitational, born from a single unified process.
And this leaves us with a really mind-bending final thought. The Delta-OO framework suggests that the most fundamental building block of reality isn't matter or energy or even space and time. It's the process of transformation itself. So what if everything we see, from the tiniest particle to the biggest galaxy, is just a temporary snapshot of this one continuous cosmic unfolding? It's a truly transformational idea to think about.